Okay, so we're going to do just a few housekeeping things before we get started with the webinar. We have a lot of upcoming events. AIPG has a lot of webinars and meetings coming up we'd like to make you aware of. This Friday, the AIPG National Executive Committee has their virtual check-in meeting that members are welcome to join at any time and be part of that. We also have a AIPG Town Hall on January 25th on Thursday. And also that afternoon, we have a AIPG section officer training webinar. And that gives new officers or current officers that have been a while and have some questions or just to get information that they may not be aware of as an officer. On January, January 30th, we have a Lunch and Earn webinar. And our Lunch and Earn series is monthly, and it is the last Tuesday of the month. And we have a student early career professional webinar February 6th. So that is launching your geoscience career webinar. So just be aware of the AIPG calendar on the website of all the great webinars we have upcoming. So the Texas webinar series is monthly and it's every third Tuesday. And today, I do want to make you aware that we have CEUs. You do need to attend the webinar for at least 50 minutes to receive the AIPG CEU certificate. And AIPG provides New York State Education Department CEUs. And to receive a certificate for New York State, you must attend the full webinar and complete and pass at 70% the assessment after the webinar. And towards the end of the webinar, I will provide a link to take you to the quiz. We also have a new survey that we have available at the end of the webinars that will give us some great feedback. We'd appreciate if you'd fill those out. So today, our speaker is John Berry, and John was editor of TPG from 2016 to 2020 and has been an AIPG CPG since 1977. He has an MA in geology from Columbia University with a focus on geophysics, oceanography, and Arctic studies. He has been a mineral exploration geologist, oil company research geologist and consultant, and has worked on 5 continents. He has worked in several thrust belts worldwide. And we want to introduce the webinar is the Messinian Salinity Crisis, Ionian Slab Rollback, and Mount Etna, how they conspire to change ancient economies and modern atmospheres. John, take it away.
Thank you very much, Wendy. Welcome to the new year, everybody. And here is the first slide. And this slide is a little bit messy, but I think you can see that it has an outline of the Mediterranean Sea imposed on the North American continent. The big fat orange line going around the outside is the boundary of the Roman Empire at the beginning of the imperial times, around 0 AD. And the 2 circles, the smaller one is 600 kilometers around Rome. And it illustrates that at that distance, Rome could not feed itself in ancient times. It was too large, had to import food. So the 600 kilometers takes in Sicily, which was one of their major granaries, and Tunisia, the Carthage area, which was another one. At 1,450 kilometers, you're able to import grain from Tripoli. And they did that. And at times they imported a major amount of grain from Egypt, which of course had low production costs because of the Nile. and that's about 2,000 kilometers out. So this sort of sets the picture and compares sort of the Roman transport situation with ours in America today. If Rome was in the Black Hills of South Dakota, they would be importing their major amounts of grain from Minnesota and Arkansas, and quite a bit from Indiana and Texas and northern Louisiana and so on, and a bit from as far away as Georgia. So the next slide shows basically the same thing, but what I'm illustrating here is I'm going to be talking about a Greek settlement called Morgantina. Actually, it was ethnically mixed. It was probably the leadership was probably a mixture of Sikh and Greek, and probably most of the population was Sikh, which were the natives of Sicily. And it got very, very rich during the late part of the Roman Republic and the early empire. And it always puzzled me how it could get so rich if it was exporting grain, because it's 85 miles from Syracuse, which was the sort of nearest, the settlement that dominated it. And it was kilometers, and 60 kilometers from Catania, which was the nearest port. And if you take the 85 kilometers and use the rule of thumb that in those days it cost 10 times as much per kilometer to transport bulk commodities like grain by land as it did by sea, then it means that Morgantina was at a great competitive disadvantage versus Tunisia and Libya, and was Tunisia and the rest of Sicily, and was competing heavily with Libya on the basin's distance, and maybe even vulnerable to competition from Egypt. There was not much competition from this northern part of the circle, because to get to those grain-producing areas in France and Britain, ships had to go around Spain, which made the route a lot longer, or you had to cross the Alps. So that made them non-competitive from the get-go. So in detail, this is a topographic representation of eastern Sicily. And here is Mount Etna. This is the plain of Catania here in green. The area to the south that is quite high is the Hyblaean Plateau. The central star is Morgantina, labeled on the smaller diagram to the right. The northwestern star there is Lake Pergusa, which I probably won't have time to get to. And the northeastern star is Monte Turchisi, or Turchisi in Italian. And that was a fortress of the same period. And the one down here is Palique, which I wanted desperately to talk about, but I probably won't get to either. So the diagram on the left here is an illustration by a friend of ours, Roine Schillingstad, a Norwegian architect who worked as an architect on the investigations of Morgantina. And this represents the status of these investigations around 1962. And you have here the agora, the wide open space, and dividing the upper and lower parts, there's this really monumental staircase here, which you can see in the background on the right, which is a view taken from a sanctuary here where I put the sort of red eyeball thing, which is looking towards the staircase. And so that's the sanctuary. And then there was a great big theater here and massive facilities on both sides of the agora for storage of grain, as well as shops. There have been some very, very spectacular art finds from Morgantina. It was not only did it have the money to build these huge public buildings, but including a huge religious building here. There's the staircase again, and this is in the left-hand slide. And here's the theater, and then these are the houses on the ridge. But this is a 7.5-foot high statue, probably of Demeter, with marble head and feet and hands, and limestone body, that was found by illegal diggers in Morgantina, was taken by a Swiss art dealer and sold to the Getty Museum, and the Getty had to return it, and it's now at Iona, in the nearest town. But there were many other fabulous pieces of jewelry and sculpture that were found at Morgantina. So it was a wealthy community, and so it must have had something to sell. The question is, what could it have to sell? To do that, to answer that, we'll talk about a little geology. So we're back to the Mediterranean basin here, and you can see that going from west to east, we have very complicated plate convergences with a subduction zone or convergence zone in southern Spain, one in northern Spain, the Pyrenees, then the Alps here, and then the Dalmatian Mountains and the Apennines, all bounded by convergence zones. And then the Apennine one curves around and ends up in North Africa. It's continuous with the Tell, the Rif, and the Atlas Mountains in North Africa. What the piece of Mediterranean that separates them is there because there's a rift valley in that through the Straits of Sicily. The Dalmatian arc continues into the Hellenic arc, and you can see the convergent rates here. There's no convergence at Gibraltar because the continents have met, but then it's 5.6 centimeters a year here, 6 centimeters a year there, 7.3 there, and near Malta, 8.1 centimeters a year. So the whole Mediterranean is closing up like an eastward facing jaw hinged at Gibraltar. The diagram on the right here is kind of confusing because north is up. The diagram was made by Tunisian geologists, and I think they're looking at the Mediterranean from the opposite side to the one that we're used to looking at it from. But they're representing here the Ionian crust, which is oceanic crust in the Ionian Sea here between the Hellenic arc and the Calabrian arc. And this is old oceanic crust, about 225 million years old, part of the floor of the Neotethys and some of the oldest surviving oceanic crust on the planet. But the shallow water here, the pale blue area, is African continental crust, which is much older. Again, it's about 1 billion years old at least. And what has happened is that because of the zone of weakness represented by the boundary between oceanic and continental crust, we have a subduction transform edge propagation fault developed along the east coast of Sicily and going down to Malta. And that's marked now by lots and lots of normal faults at the surface, and in 3 dimensions going deep is this diagram represents what's happening. The step, the subduction transform edge propagator fault is this thing here between the oceanic and continental crust, and this thing here. And the Ionian crust is dipping down steeply. Oops, what happened? How did that happen? Beneath the Tyrrhenian crust, and this scissor thing has happened here. By the way, the Ligurian Basin is pretty old too, and you can see that's got a smooth floor as well as the Ionian Sea has a smooth floor. The Turanian crust is only 1 million years old, and that's not had time to get any sediment on it, so it's very rough, but it's the overriding crust in this part of the world. So the next slide here, which accidentally I got to, shows the surface geology of Sicily with the steppe, this whatever it's, subduction, whatever thing, scissor-like fault, going almost underneath the summit of Etna, and then intersecting with the Tyrrhenian plate here. This is the Ionian plate, and then here we have the Hyblaean Plateau, which is another area of partly of volcanic rocks, and that's south of Etna, and that is where the Etna volcanism was from about 2 million years ago until about 500,000 years ago. This was where the major amount of volcanism was, and that's shown by the red colors in the diagram on the upper right here. So that's the Hyblaean Plateau, and it is still rising. It still has a big magma body below it that is buoyant, as is Etna. Then we have the major plate convergence up here along the north coast of Sicily, but the leading edge of the thrust front runs through here and also runs very close to Etna. Over the top of that thrust belt is a series of post-tectonic basins that together form the Caltanissetta Basin, and these basins are full of the evaporitic deposits laid down in the Messinian event. Here's Morgantina, and then in front of the thrust belt, the Jela thrust sheet, is the Jela Catania foredeep, which is the foredeep being weighed down by this migrating thrust sheet, as well as by subsidence between Etna and the Hyblaean plateau. And here we see on the right, this is all illustrated in much more detail, but showing also all the faults, the minor faults and whatnot. It's incredibly complicated. And then the steppe is represented by this sharp scarp into deep water off the east coast of Sicily. So now I'm standing in the ruins of the castle at Idona, the nearest town to Morgantina, just about 8 kilometers away. And the Morgantina site is on this hill here. Then that is the sort of edge of the highlands in the thrust sheet. And then we have this hilly area, which is still in the thrust sheet, but mainly very soft rocks and so eroded away. Behind these marly hills, we have the Ionian Sea, part of the Mediterranean, and behind that on the left, Mount Etna, with kind of a nasty sulfurous haze over it, partly probably due to the presence of the large city of Catania, but partly due to Etna, which is almost continually erupting. And here, I think these little puffs of cloud over here are actually puffs of whatever that Etna had recently given off at the time of the photograph. So I talked about these post-tectonic basins within the thrust sheet that make up the Caltanissetta Basin, and here's a cross-section through them, and they're full of these 2 cycles of Messinian evaporites. And in the deeper parts of the basin, you have sylvite, you have potash salts, which have been mined, and then you have halite, extensive halite, which you never see, of course, at the surface, and then gypsum, which is what you really see. in a second, mainly laid down in a second cycle of evaporites. So this is the lower cycle gypsum here and gypsum and turbidites here. And then the lower cycle is in yellow over here, but the pink is the upper cycle. And covering this is a layer of sandstone, which truly is post-tectonic because the deformation is basically stopped, basically undeformed, and then the Truby Formation above that. The cross-section line is from A to AA, so it goes from the north coast of Sicily to the Hyblaean foreland. And the black areas on the map are where areas in these deep basins where you have halite and potash salts. The last place I talked about, by the way, was the Belice Basin, which is up here. The outline of Sicily is hard for me to see, but it's this. So what did it look like in Messinian times? Well, this is an artist's impression. There's the States of Gibraltar labeled with A, and the Sicilian Channel labeled with B, with F, with its rift valley. And this is the western basin of the Mediterranean and the eastern basin separated by this high through Sicily. But the artist didn't have good geological advice because Sicily has Messinian deposits on it. So most of Sicily at the time was below the water. It's probably just the north coast was blocking connection between the two parts of the Mediterranean. And looking at it from the Straits of Gibraltar, you're looking through the western basin here, and there is Sicily, and then underneath the little thing, here we go. Then there's a channel connecting to the eastern basin here. The eastern basin had much more evaporation. I used to think that, envisage that when the Messinian period ended, that the Straits of Gibraltar had a 4,000-foot high waterfall, but that's not true. Number one, you don't need to evaporate all the water in the Mediterranean to get these salts, even sylvite. Number two, it's been documented that this was a very steep river valley rather than a waterfall. But at the Sicilian end, between the two basins of the Mediterranean, this white patch here really was a waterfall, and there's a huge chaotic deposit of giant boulders and rocks near Malta, just east of Malta, which represents deposits from that waterfall. So here's what, again, on the left, the overall map. And I'm going to be looking first at this little area here near the Greek city of Agrigento, because I've been there, for one thing, and seen these potash mines. These mine galleries in the lower right thing here, little square things, are about 500 meters down in some cases, so 1,500 feet, and nasty places, and they're reached by tunnels about 4 feet high, consisting of hundreds and hundreds of steps going down at a very steep angle. And these tunnels had to be traversed by men and boys as young as 6 years old, carrying the ore out of the mines. And you can see how the first cycle of the Messinian deposits is very, very deformed compared with the second cycle, which overlies it unconformably. So this whole Messinian thing, we sometimes fail to realize, was going on in the middle of all this tectonic deformation. There's another view of some of the deformation. And if we look at the upper cycle rocks, they are also deformed, not as badly, but this is gypsum. This is a vertical wall of gypsum, almost like a dike of gypsum, although I think it's probably on a thrust fault, a deformed thrust fault. And here it has the Castello di Gresti, which is written up in tourist brochures as a medieval castle, but in fact, it's, at least in its latter phases, it was a sulfur mine. And because the gypsum is impregnated almost everywhere with sulfur, which forms by bacterial action on the calcium sulfate when the calcium sulfate gets into a weathering environment. So they put a shaft down inside the gypsum here and mined the calcium sulfate, again under incredibly bad conditions. But get to that later. But here's this another ridge of gypsum. Here are some ovens. The black things are the mouths of ovens where they were burning or heating the gypsum to melt the sulfur and drain it off. And these ovens are everywhere in the countryside of this part of Sicily. This is an outcrop near the ovens where you had primary anhydrite deposited. And when it hydrated at some later diagenetic stage into gypsum, we got this deformation here, which is very similar to what we have in the lower Edwards in the Austin area. We call them teepee structures there, but these seem to be upside down teepee structures. So that's one outcrop, and then here's another outcrop. And on the left slide, it's illustrating chicken wire anhydrite, where you have blebs of anhydrite growing in an organic kind of situation. And so they are surrounded by a fine reticule of organic matter. And they're kind of nailed in place by this organic matter. When they weather, you get this sort of situation you have here up to the upper right on this block. The right-hand picture, on the other hand, shows some of the involved situation where you have gypsum being deposited in very shallow water and interleaved with very fine siliceous dust that's blown in, and with very fine clay. So these are the conditions in the mines. On the older photographs here were taken around 1900, and this shows boys hauling loads of 20 to 30 kilograms, which represents 50 to 65 pounds of material on their backs out of a mine. And inside the mine, the temperatures were over 45 degrees C, and there was very little ventilation, and the atmosphere was bad. So the guys are working completely naked underground here. The lower left photograph shows the people in uniform or Red Cross personnel, and I'm pretty sure that that's a mine car there, an ore car, and in it is, I think, a dead body that's covered over. The conditions were awful, and all of these images came from a special exhibition of material, geologic and photographic materials collected by a very famous local geologist. So the surface conditions were almost as bad. Here's one of the vents for one of the ovens, and it's about a foot across in diameter, in cross section, taken by me. And then here's a picture taken again in the late 19th century or early 20th century of these surface ovens burning the sulfur-bearing rock and giving off ghastly clouds of SO2 and H2S that people had to live in. I mean, these were, the communities were right there. Booker T. Washington, the American Black scientist who must have had experience of some pretty atrocious living conditions in parts of the US, visited Europe and wrote in his book about his visits to Europe, written in 1912, "I am not prepared just now to say to what extent I believe in a physical hell in the next world, but a sulfur mine in Sicily is about the nearest thing to hell that I expect to see in this life." pretty grim, and it's affected Sicilian politics and art and literature since. Pirandelli, who's a famous Sicilian playwright and author, still hates the British because, and he's very left wing because he saw all these conditions as a young man. And he still hates the British because of the way the British and French owners of these mines used child labor that was practically slave labor. By the 1970s, conditions were improving, and here's a modern system with one of these ore carts that was automatically hoisted up and then put on rails at the surface and the ore dumped. These are back in the 20th century ovens in this same area. Floristella and Grotta Calda is a mining park near to Morgantina, not very far at all from Morgantina, that has a very, very interesting exhibitions about this whole thing, and a mine you can visit. This is one of my colleagues, and we're looking at, he's looking at a warm spring in Grotta Calda, which is giving off this milky colored, bluey, milky colored, stinky, hot, warm water. And he's sampling the water. So now to Etna and how it connects with this. And one of the key facts about Etna is that it is responsible for 10% of the worldwide volcanic emissions of both SO2 and CO2. And I think you're beginning to maybe see the reason that there's a lot of SO2 and CO2 in this volcano. It erupts all the time, and it sometimes blows smoke rings. This is one on Christmas Eve in 2018. And below that is a picture from space of a plume of sulfur dioxide. It did on the 25th of March, and I got this from the BBC. And you can see it's pulsing, this plume. It's not a continuous plume. Here there's a little gasp that gets blown south of Etna and for a ways. And then before that, there was another gasp that was blown further south, but before that had been blowing east. And then maybe 24 hours previously, there was this giant blast, which forms a plume that curled around, had a big mini blast there, died off a bit, and then had a major blast here, which is sitting right over Cairo and the Gaza Strip. The Gaza Strip is the very worst part of this blast of sulfurous atmospheric gas. And you can trace these sulfur plumes, these SO2 plumes from Etna all the way to China from space. Now, this is sort of the basic plan of Etna. The pink is the lava. The green is the fold thrust belt rocks that are with lots and lots of evaporitic minerals in them. And the pale green is quaternary clays deposited along the coastline. And you can see that it extends, it's unfortunately got another box over it, but it extends fairly far westward there. And again, this illustration of how Mount Etna is in the thrust belt and on this incipient plate boundary where this step fault is occurring. Some other important things to know about Etna is that this entire south and eastern part of the mountain is unstable, and there are lots and lots of surface fault indications that it is sliding off to the southeast much faster than the rest of the mountain. But the whole mountain is also sliding southeast at about 14 millimeters a year on a plane that dips about 6 degrees to the southeast, or more to the southeast actually, and is composed of intervals of shaly and scaly and sulfurous or evaporitic rocks. And so here are some of these faults that are along which the mountain is beginning to fail. And you can see there's left lateral transform motion on that fault, and there's right lateral transformation on these faults. And there's normal faults that show how it's sliding off. This Valle del Bove is a valley that was created by a lateral blast, a Mount St. Helens type blast about 8,000 years ago. And you can see how the headward, and it's associated with this, the peak of this failure, which is, and the amount of motion, the amount of failure faults are concentrated near the summit, which is labeled with the CC here. There's the summit. CC is in that inset, that black and white inset up there, and you can see all these craters here. So this is what this looks like geologically. This is sort of schematic, but we have the thrust belt with the green is the continental upper crust. Sorry, it's not. Sorry, the green is the sedimentary covers of the Pelagian block, the deep block. So this is autochthonous, it's not crust. It's autochthonous sedimentary rocks, and it's largely carbonates. So the eruptive material of Etna is coming through this big pile of carbonates that's in green here. The blue is the covering of that, which is largely shelf sediments, again, very much carbonate, but a lot more clay and whatnot that is pushed over the top of them. And the orange is this upper Miocene to Plio-Quaternary sequence that contains the Messinian salt. And you can see it forms a big décollement, which itself is disrupted by the main fault. Underneath all of that allochthonous shelf material and continental slope and shelf material. And then it's deformed by the Jala Nap, which covers the surface in the Catania 4 deep. The whole mountain lies over this, and AS is argile scaliose, which is subduction-related serpentinitic scaly clay, and is very non-resistant to shear. And the yellow, of course, is got a lot of evaporites in it, and the N is Numidian flysch, which again is a very, very soft, shaly rock with well-developed bedding and not very resistant to shear. So here's this huge edifice of Mount Etna, all 4 kilometers height of it, sitting on this stuff, sliding off to the southeast, which is to the right, and also spreading under its own weight because it's got such a frictionless base that it can be shown to be spreading. And that section line is a due north-south line from the Tyrrhenian Sea to the Himalayan foreland. It doesn't show the volcanics in the Himalayan foreland, which again is largely a carbonate sequence. So basically, everything that's coming up through Mount Etna and being blasted into the atmosphere is passing through a huge thickness of carbonate, several kilometers, many kilometers, 10 or more, and through evaporitic rocks. So no wonder it's responsible for a major part of the volcanic emissions of sulfur and CO2. This is a more detailed section in a different line. It's further to the west, so it doesn't go through Etna, but it does show more clearly and this is why I said upper crust by mistake in the other one, because here it is. The yellow does represent the upper crust, so the green represents the platform cover, continental shelf and margin cover. But the MP is the Miocene, Pliocene evaporite sequences, some of which are right directly underneath the mountain. And the NF is the Numidian Flysch, all of which is very deformable. So, and that, by the way, those two last diagrams, this is 1-to-1 scale and no vertical exaggeration. And I meant to point out that I'd always had difficulty envisaging how something, a thin sheet from something like the Tyrrhenian Sea, which is 4,000 meters deep, could be pushed over Sicily, which gets to be 3,000 meters high. You realize how insignificant those depths and those heights are, because the thing that's being deformed is more like 20 kilometers deep altogether. So what we're seeing at the surface is only a very minor part of it and should not influence our mental pictures of what's actually happening. So again, it's a little more here on the little thing at bottom left here. The pink colors represent deeply buried, more than 3,500 meters down to the top of the carbonate successions, the autochthon. The green is shallower material. And you can see that Mount Etna occurs right on that transition. And it also, because Mount Etna is rising at several centimeters a year, it interrupts that Yala 4 deep there and brings things closer to the surface. Here are the volcanics in the Himalayan plateau. This is the best illustration I have of that. And since this is rising again because of a light magma underneath it, you can see how the resistant volcanic ridges in the northern part of the Himalayan plateau are getting buried underneath the Holocene sediments of the Catania plain. This is the Jala Nap. This is the steppe, which is now this part of it is called the Malta Escarpment Fault System, but it carries on right across the northern coast of Sicily. This is the failing part of Mount Etna because it's feeding right into that fault system. And again, there's the surface map, and I've repeated this to oh, and this is a very nice, I'll talk about the left-hand side first. This is a very nice cross-section of Mount Etna showing the early, the pale blue is the sedimentary basement. The darker blue is the early basalt phase from 500,000 years ago until 30,000 years ago of Mount Etna. And then 30,000 years ago, it started to become a stratovolcano, and you have these sort of 3 distinct stages of that phase of stratovolcanism, and then it got very violent, and you had a lot of violent eruptions, and they formed this Montebello stage, and then the most recent stage is the orange. The green is the Montebello. The reddish cross-hatched area is the Valle del Bove caldera fill. And that's exposed at the surface, and that's why we can map the structure of Mount Etna. And that's only 8,000 years old. And now you can see on the right, though, how sparse the evidence is that enables this picture to be built up. Those these dark blue things here from the early basaltic volcanic system, they just occur here, a little bit in the walls of the Valle del Bove and down here at this point, and I think a couple of points over here. The brown tholeiitic system is only really exposed here and here. and nowhere else. So you have to, it's been very, very, the geology has been very, very carefully built up. And then we have the stratovolcanic here, there's lava flow, ignimbrites here. I tried to do my own work on figuring out just where the coastline was 2,300 years ago when Morgantina was in its prime. And so I plotted a lot of stream profiles, and that this big yellow circle is related to that. But I also noticed that there's something very funny happening around Etna. All of the rivers around Etna everything flows in a circle. I mean, not all the same river, but everything is diverted by either the lava of Etna or the deformation going on, so that the watersheds follow a circle that is about 45 kilometers radius around a point about 11 kilometers south of I think it was 11, maybe I was wrong here. No, 21 kilometers south, about this yellow point here. That's the center of this radial series of watershed boundaries. Everything inside that circle drains first towards the mountain and then off to the sea here. So I think there's something fundamental there, and what that it's not really mentioned in any of the literature I found. They're all focused on the local uplifts here and there, but I think probably part of that circular feature is due to there's an isostatic load due to Etna, and that has not been well described. But I figure that since Greek times, there's been about 20 meters of isostatic sinking, which is, of course, offset by rising under the mountain itself due to the intrusion of its source magma here, and it's offset by rising here. But it must be causing some deformation that has controlled the way the erosion takes place. The parallel lines down in the southeast west corner here are the tilting of the quaternary alluvial fans that fed to or shorelines maybe, so that they go up to about 1,000 feet, 1,000. No, yes, 1,000 meters here. No, it can't be 1,000 meters. I'm sorry. I failed to label them, but and then here, these are definitely 10-meter intervals here. So we have 10 meters, 20 meters, 30, 40, 50 meters. And by the time you get to that fortress I mentioned, Monte Turquisi, you've got 50 meters elevations here. By the time you get to Morgantina, the river is at 600 meters. So this alluvial thing has a very flat but noticeable slope, and then it steepens up going out. And this is reflected in the settlement history. Every one of these blobs represents settlements of a different era that has been archaeologically investigated, and I've drawn lines showing where the nearest ones are to the to what was either a coast, probably a coastline at the time. And so this short dashed line is the oldest, the archaic era settlements. This one is the classical era. This one is the Republican era. And they migrate into the Catania plain as they become younger. And they particularly migrate at this end of the plain. So this suggests that the west end of the plain has been rising more rapidly than the northern and southern flanks even. So the thrust movement may be the most important movement governing the evolution of the plain. The lines here do not coincide with the settlement distribution, because these settlements are actually in a valley north of a cuesta of deformed Pleistocene sediments, which is here. If you can see on the right, there's a row of there's a dipping ridge, southward dipping ridge here. And those settlements are all north of the ridge. So I didn't draw a shoreline through them, knowing that there was a ridge there. So here are the stream gradients, and you can see my yellow circle was at 40 kilometers from the mouths of the rivers. There's the 40-kilometer mark, and you're getting about a 0.2% gradient from there to the sea, no matter which way the rivers are flowing. These rivers in the top diagram are flowing from the northwest, and these are flowing from the due west. And the Gornalunga is sort of the bound, that's the river that flows to Morgantina, and so I put it on both diagrams. But you can see all the rivers have very similar gradients, except for the biggest one, the Simeto, which is flowing in a circle around Mount Etna, and it's been blocked by lava at two places. So it's got two very prominent nick points that bring it up much higher. But all the other rivers have similar gradients, except for the Gornalunga. And it's much steeper than all of the rest for the reason I suggested, that I think in its western reaches, the deformation of the thrust sheet has been more important than the uprising of the volcanics. There is Morgantina, and the Ventrelli and the Monarchi are very, very small rivers. So from 40 kilometers to 65 kilometers, the gradient increases to about 0.3%, and then from 60 on, it's much too steep. This I did a lot of work in Western Sicily on about what river gradients you needed to be able to use the rivers for transport. You have to remember that in Greek times, the soil still existed and there was still a fair amount of forest around. So you had base flow in winter. And so you could use 0.2% gradient. If it existed then, could be used for transport. But I suspect that this actually marks the ancient coastline. So that yellow circle goes through the points where the coastline went most inland in Greek times. This is this famous Monte Turchisi. I keep mentioning. It's there on this river valley, overlooking the plain. It's a huge defensive work of Hellenistic age, so late Greek age, and it obviously was built to command any threat or any transport of goods through this part of the plain of Catania. And it suggests to me that the shoreline was very close to it at that time. And there's also a Roman villa, which is not on this map, but there's a Roman villa about there, which probably served, it's not quite as militaristic, but it seems to have been very wealthy. It might have been acted as the supervisor for a port facility on the river going to Morgantina. And that's, so the answer to the question is, how could they support themselves on grain exports? To me, is the fact, it seems to be that the coastline was much, much more closer to Morgantina in Greek times than it was now, and than it is now. And in fact, the entire central part of the plain, today's plain, was probably open water, and then each river probably had an estuary that went several kilometers further into the land, at least as far as Monte Turchisi, and probably as far as just opposite this town, Ramacca, on the Gornalunga River. And I had to do a lot of work to come up with not very much thrilling in the way of results, but the getting there was interesting. Thank you very much. Okay. Thank you, Wendy.
Oh, thank you, John. So let's see. I know we have a few questions in the chat, and
So
if anybody wants to raise their hand to ask a question, we can do that as well. So we have one here, Don Ruggery. So how far away is the current coastline to be from Monte Terzizi?
from Morgantina to the current coast is 60 kilometers. And I hope I didn't mix miles and kilometers when I was talking about the radius of those circles. Everything should have been kilometers.
Let's see. Bill Turner says water level in the, you're going to probably have to read through these. Are isostatic sinking?
Sorry?
Let's see.
I can't see the point now. The isostatic, yes, the isostatic adjustment, I calculate that that an area extending out as far as that as this circle, at least as far as this circle has been sinking, and that that would be based on the rates we have from glacial isostatic rebound in the northern hemisphere. That would amount to about 20 meters since 2300 BC. Not that much, but it's on the same order as the uplift of Mount Etna.
So Bill Turner also asks, are the carbonates chalk or real limestone?
No, it's not. It's if you're familiar with the Austin chalk would be hard compared with some of these late tertiary chalks and marls in this area. They're very soft indeed. And in fact, all the soil has gone away and the farmers plow these rocks routinely.
Is there subsurface borehole conformation of the cross sections?
Sorry?
Is there subsurface borehole conformation of the cross sections?
The big brightly colored cross sections I showed are based on seismic data. There is borehole conformation for the some of the other cross sections I showed, which were more local.
Okay. Are the volcanics basalts of andesites?
No, they're not andesites.
Okay.
They're much more basic. Everything is more basaltic, and starts off as stalactitic and ends up as just basalt.
Okay.
So
seeing if there's any other questions.
I haven't seen. I'm looking through them too, and
okay, good.
Agora, yes, I know. My wife is always connecting me on pronunciation. Yes. No, there is this. Everything goes far to the east, but I wasn't considering that.
Carol, you don't need to ask for the certificates. You will receive the AIPG certificate since you were on the webinar, the full duration. If you want the New York certificate, you need to do the assessment quiz.
Yeah, replying to Bill Turner, are the evaporites in block faulted grabens, or are they as they are in Cyprus? No, they're not. They're much more folding in Sicily, but there are block grabens. But the place that you really notice them is in the Himalayan uplift, which doesn't have evaporites. But in the fold thrust belt, they're basically in these post-tectonic more and the margins, rather than block fault, it will have a thrust fault as one margin, or be over a thrust fault. Yeah, no, and no, it's not like Cyprus at all. These are oriented east northeast to west southwest.
And just the link.
Yeah,
the
Bill,
link for
right.
the.
Sorry.
Oh, I'm sorry, John. Yeah, the link is in the chat box if anybody wants to do the quiz to get the New York certificate. Just so everybody is aware, the link is in there.
Bill Turner was talking about water levels in the Med are up from 2,000 years ago. Yes, they are. And I'm finding it difficult to deal with this. For example, in the east edge of the Himalayan uplift, they're talking about uplift rates of 0.8 to 1.3 millimeters a year, but the sea level has been rising faster. And I pulled one illustration, which I didn't use, which shows this complicated eustatic sea level curve with lots of wriggles on the top once it gets into the Holocene. And I have a little trouble with that, because in other places, and even in this same area, when I was looking at Western Sicily, the people there were using a eustatic sea level rise curve that was much simpler and didn't show these wriggles in the Holocene. But it seems to be routinely accepted in Eastern Sicily that Eustacy was different, and that's not reasonable. So, but you know, and yes, they find amphory in this part of Sicily. They find Greek amphory upright in situ, and Greek harbor installations down several meters below current sea level. The current coastline from Monte Turcisi would probably be, there's Monte Turcisi, about 30 kilometers east of Monte Turcisi. By the way, the current coastline is not very stable. It was further east in the Victorian era, and then they started building dams on the rivers and cutting off the sediment supply, and the coastline has been retreating of recent time. Okay, Ross, thank you. I wasn't very clear on this. I'm answering a question by Tony Giunta here. Giunta, I should have been much more clear about the fact that neither potash nor sulfur nor any salt they might have mined here was a valuable export in classical times. The market for sulfur developed in the Byzantine era when they started using it for Greek fire. The market for potash is even more recent than that. So the mineral exports that I thought when I started looking at this would have been a basis for their economy really could not have been a basis for their economy. It had to be grain. The soils of Sicily are pretty awful right now, because we've had from roughly 2,700 years of bad farming practice. So there's really no soil left in most parts of Sicily. The joke is that they farm the bed, they plow the bedrock, and that's very true in the lowlands around Morgantina. So yeah, and the grains that they exported were basically barley and wheat, with wheat by far the most dominant. And somebody made a comment about Syria being the granary of Rome. I'm not sure how important that was at these times. The Romans had to go further and further as time went on, and for a long time, Sicily was their main. Around 300 BC, Sicily was their main granary, and then I believe there was a period when North Africa was extremely important, and then there was one brief period when Egypt was really important. But and one of the things that I'm trying to get a handle on, but haven't been able to, is how much surplus the average grain farmer in this part of the world had. But because under the Sekel government of Morgantina, everybody had to contribute a tithe of everything they grew, and that got exported to make money for the government. But at times the Romans demanded 2.5 times that, so a quarter of everything everybody grew. And how much, whether the peasant farmers could sustain that, I don't know. The Romans never did it for very long. Let it go. Yeah. So buried in cemented beach sands. Yeah, Bill Turner, right. Yeah. Huh. Okay. Tony Giunta from Messina. Yeah. Okay. Thank you. I think I got to the end of all the questions. Thanks.
Great job, John. Very good.
Thank you.
All right. All right. We'll go ahead and end the webinar. Thank you very much, everyone.
Thank you very much, everybody, for attending, and thanks for the nice comments in the chat. Okay.